Hi girls, today we're going to start with Lesson 2, Applications of Induced Currents. In Lesson 1, we studied electromagnetic induction, and we saw how moving a wire in a magnetic field will generate or induce a current in that wire. We also calculated the electromotive force, or the voltage induced on the ends of a wire moving in a magnetic field, and we also talked about the two applications of induced electromagnetic induction, which are the microphone and the generator. After that, we moved on and we learned how to find the maximum power generated by an AC generator, the average power, and the effective electric potential and current values as well. In this lesson, we will talk about these objectives. In the first objective, we will state and practice Lenz's law, and then in the next lesson, we will mention the effects of Lenz's law on different devices. After that, we will explain the working principle of a transformer and calculate different variables in it. So let's start with objective 1 and see what is the statement of Lenz's law and how does it help us find the direction of the current in a coil of wire. Before we start with the lesson and Lenz's law, you must remember the three right-hand rules that we have taken in term 1. The first right-hand rule was to find the direction of the magnetic field around a current-carrying wire. In this rule, we will have a current-carrying wire. For example, if we have this wire like this, and we have a current moving in this direction, then a magnetic field will be generated around the current-carrying wire in the shape of concentric circles that move further and further away from one another as we go further from the wire, just like this. Now the direction of the magnetic field can be found using the first right-hand rule, where the thumb shows you the direction of the current, and the four fingers will show you the direction of the magnetic field. In this case, it will be going in this direction, rotating around like this. From the back of the wire, it will be going in the left direction, and then from front of the wire, it will be going to the right, and so on. It goes like this. The second right-hand rule we talked about in term 1 is to find the north pole of an electromagnet. Remember, an electromagnet is a coil of wire that is connected to a battery. Once it's connected to a battery, current will start to flow in the wire, and this coiled wire will become an electromagnet. That means it gains magnetic powers. Now it will be able to attract metal things like paper clips or nails. We learned how to find the north pole of this electromagnet. Remember, this is similar to a magnet with a north and a south pole. We learned how to find the north and the south pole of an electromagnet using the second right-hand rule. Let's draw an example just to remind ourselves with the concept of an electromagnet. Let's say that this is an iron core, and around this iron core we have a coil of wire, and this wire is connected to a battery, the positive side and a negative side. Now we know that the current goes out of the positive side. From the back of the iron core, it would be going upwards, and then it coils in front of the iron core and then goes downwards and then backwards and then downwards again. So from the side that you can see from the coil, the current is moving downwards. Now you're going to put your four fingers in the same direction as the current, the one that you see in front of the iron core, and the thumb will point in the direction of the North Pole. So now this coil has become an electromagnet with a north and south pole. This would be the north pole, and this would be the south pole of this electromagnet. Because if you put your hand in the same position, the current is downwards, you'll see that your thumb is pointing towards the right. So this side right here of the electromagnet is going to be the north pole, and this side is going to be the south pole. The third right-hand rule we have taken in term 1 was about the magnetic force. To find the direction of the magnetic force using the third right-hand rule, we're going to put our thumbs in the following directions. The thumb should be in the direction of the current. The forefingers in the direction of the magnetic field. The palm of your hand will show the direction of the magnetic force. Just a quick example on that. Let's imagine that we have a magnetic field that goes to the right like this. And we have a wire. And this wire is carrying a current. And this current is moving downwards like this. Now, if we put a current carrying wire in a magnetic field, it will be subjected to a magnetic force, just like we saw in the lab. And it's going to be pushed in a certain direction, which we'll find using the right-hand rule. So, using the right-hand rule, you're going to put your forefingers in the direction of the magnetic field, which is to the right, and the thumb in the direction of the current, which is downwards. If you do so, you'll see that the palm of the hand is pointing out of the screen or towards you. Hence, we're going to have a magnetic force that pushes this wire out of the screen towards us. So the force is going to be out of the screen. So this is just a reminder for the 3 right-hand rules that we have taken in term 1. The first one, to find the direction of the magnetic field around the current carrying wire. The second one is to find the north pole of an electromagnet. And the last one was to find the direction of the magnetic force for a current carrying wire placed in a magnetic field. So let's start with Lenz's law. Let's imagine here that we have a magnetic field that goes into the screen. You can see that X's in green. That means that the magnetic field line is going into the screen, away from you. And we have a U-shaped wire here, and we have a straight piece of wire on top that we're going to pull down so that it forms the closed loop of wire as it goes into the magnetic field. Now, as the current starts moving in the magnetic field, as the wire moves in the magnetic field, a current is induced in that wire. According to the electromagnetic induction rule, if we have a wire moving in a magnetic field, cutting through magnetic field lines, a current is induced in it. And we can find the induced current using the right-hand rule. This is the right-hand rule that we learned in lesson 1. We said that to find the direction of the current, you have to put the thumb in the same direction as the velocity. The forefingers must be pointing in the direction of the magnetic field. Hence, you'll get the direction of the current shown by the palm of the hand. Now let's position our hands to find the direction of the induced current. Of course, we're going to use the right hand, not the left one. Now we're pulling this wire downwards, hence I'm going to put the thumb downwards. 1 minute. All right, there you go. So the thumb is down, and the 4 fingers, which shows the direction of the magnetic field, should be into the screen, pointing away from me, just like that. I don't know if it's clear under the white background. I'm just gonna do this, center back so that you can see. All right, so you can see the thumb pointing down, the 4 fingers are pointing into the screen. The palm of the hand, as you can see, is pointing towards the right. So here, the current would be pointing towards the right. So in this piece of wire, once it moves and cuts through the magnetic field lines, you can see that the current in it is moving towards the right. But remember that if we have a current carrying wire in a magnetic field, according to right-hand rule 3, a current carrying wire in a magnetic field will have a magnetic force applied on the wire. Hence, now because we have a current carrying wire moving in a magnetic field, we will have a magnetic force. And we can find its direction using right-hand rule 3. We're going to put the thumb in the same direction as current. I know it's a bit confusing using like 3, 4 right-hand rules at the same time, but it will reduce into one, I promise. And the 4 fingers in the same direction as the magnetic field. The palm of your hand will show you the direction of the magnetic force. So let's position our hands to find the direction of the magnetic force. Now we have established that the current is towards the right. And the magnetic field still as is towards the screen or into the screen. If you position your hand such that the thumb is to the right, direction of the current, and the 4 fingers in the same direction as the magnetic field, which is into the screen, you'll see that the palm of the hand is pointing upwards. So the direction of the magnetic force will be where? It will be upwards. So that means that when you try to pull this wire into the magnetic field, you'll feel some resistance as if someone's pulling from the opposite direction. Real life is just the magnetic force trying to stop you from moving that wire. So we can say that when moving a wire, a current is induced, and when we have a current carrying wire in a magnetic field, it will be affected by a magnetic force upwards in the opposite direction of motion. You can see the video as total, so induced current carrying wire in a magnetic field will have a force in the opposite direction of motion like this. So what is Lenz's law? Lenz's law states that the magnetic field produced by the induced current is always in the direction that opposes the change in the original field or the field that induced it. Now this is a really complex statement. Let's break it down. We already established that moving a wire in a magnetic field will induce a current in that wire. Now, this wire that's carrying current will induce its own magnetic field. So, shown in the green crosses is the original magnetic field that induced the current. And shown in purple here is the magnetic field induced or generated by the induced current. So now we have two magnetic fields, the original one that was responsible for inducing the current and the one that the current carrying wire is now inducing. You can see that it's in the shape of loops around the wire. Now, Lenz's law states that the magnetic field produced by this current carrying wire will always be in the opposite direction of what happens to the original field. So, for example, if we take this straight wire and move it downwards, just like this, 1 minute. Oh, it's not showing. So if we take this straight wire and move it downwards, the number of the original magnetic field lines in the loop will increase. Imagine it with me, pulling this, let me show you. Pulling this wire downwards will mean that we will have more X's in the loop. That means that the magnetic field, the original magnetic field inside the loop has increased. Now, the current induced in the wire will try to decrease the original field. by generating its own magnetic field in the opposite direction. This way, we will have two magnetic fields in the opposite directions that will yield, if you add them together, for example, it's like adding a positive and a negative value, like +5 and -3, that gives you 2. So that means that the total field will decrease. So the magnetic field produced by an induced current is always going to be in the direction that opposes the change in the original field. If the original field increases, then the induced magnetic field is going to be in the opposite direction to try to decrease it. And the opposite is true. If the original magnetic field, the one in green, decreases in the loop by moving this wire upwards, then the induced magnetic field, the one in purple, is going to try to increase it by being in the same direction. So that both of them in the same direction, they're going to add up. It's like 5 plus 3, that's going to be 8. So in Arabic, يكون اتجاه المجال المتولد من التيار المستحث بحيث يعاكس التغير في المجال المسبب له. إذا زاد المجال الأصلي، المجال الجديد اللي باللون البنفسجي راح يحاول يقلله فبيكون في عكس اتجاهه. أما إذا قل المجال الأصلي في الحلقة فالمجال الجديد راح يحاول يزيده فبيكون معاه في نفس الاتجاه. So let's repeat. If the magnetic field inside the loop increases, by pulling this wire downwards, we increase the number of axes, which is the original magnetic field inside the loop. If that happens, a current is induced in the wire, and this current is going to induce its own magnetic field, the one in purple, and it's going to be in the opposite direction of the original field to try to decrease it. دايما بتعاكس التغير، دايما بتحاول تحارب التغير. المجال الأصلي ازداد، راح ينشأ واحد يحاول يقلله فبيكون في عكس الاتجاه. But if the magnetic field inside the loop decreases by pulling the same wire, instead of downwards, if we move it upwards, the number of axes, which shows the original magnetic field, will decrease inside this blue loop. When it decreases, a current is induced in the wire such that it induces its own magnetic field, which is shown in purple here, and it's going to be in the same direction as the original field. So you can see here its axis. You can see that the magnetic field induced by the current carrying wire inside the loop is also axis, which is into the screen. So the original field decreased. That means that the induced magnetic field is going to try to increase it back up by being in the same direction. Okay, how do we use this in the exam? Remember the electromagnet that we talked about earlier. So here we have a solenoid, and the solenoid is wrapped around an iron core, and it is attached to an ammeter. Now, if you take a piece of magnet, you can see here we have the North Pole, and you approach the North Pole towards this solenoid, the magnetic field lines will cut through the solenoid, generating or inducing a current in it. According to Lenz's law, when we approach the magnet, you can see here we are approaching the North Pole. The magnetic field inside the coil will increase. So because we are pulling it closer, the number of magnetic field lines crossing this solenoid will increase. So the magnetic field inside the solenoid will increase. So a current is going to be generated in the coil, in the wire, such that it will try to decrease the magnetic field. So it will induce its own magnetic field, and it's going to be in the opposite direction of the original field. So you can see here that this solenoid generated its own magnetic field. And this magnetic field is in the opposite direction of the original one. So the original one was going like this. And it was approaching this solenoid. So it was increasing inside the solenoid. So it tries to defend itself by generating its own magnetic field, and it's going to be in the opposite direction of the original one. So it will generate a north pole here, and hence the other side would be a south pole. Because here the magnetic field lines are exiting, that means that this is a north pole on the electromagnet or on the solenoid, and this will be the south pole. And hence you can see that there's a repulsion force between the solenoid and the magnet. Now, using the right-hand rule, you can find the direction of the current. We're going to use right-hand rule 2 to find the direction of the current inside the solenoid. Now you're good. Put your thumb in the same direction as the north pole. And the four fingers, the four fingers will wrap around like this. So these are you're going to see your nails like this. That's a really ugly hand. Oh my God. Used to be an artist. Oh, anyways. So you can see that the direction of the current is going to be downwards from the side that you can see from the solenoid. So it's going to be down like this. So it's going to move like this and go through the ammeter or galvanometer, the opposite side, and so on. So Lenz's law is used to find the direction of the current in a solenoid. Let's see the other example. So you can see here, we have a magnet, a north pole approaching. This solenoid freaks out, generates its own magnetic field, and is going to be in the opposite direction, trying to push it away, just like a child trying to push a toy forced on him. And hence it will generate its own current. And we can find the direction of that current using the right-hand rule too. Going to put your thumb in the same direction as the induced magnetic field, not the original one, the one in purple, the induced one. And the four fingers will show you the direction of the current in the solenoid. Okay, let's see another example. What happens when we take the magnet out? When we take the magnet out, surprisingly, now he wants the toy. Once we took the toy away from him, now he wants the toy. Similarly here, when we pull the magnet out, the magnetic field inside the loop will decrease. You'll have fewer number of magnetic field lines going into the loop. So the total magnetic field will decrease inside the solenoid. And hence, a current will be induced in the solenoid that induces its own magnetic field. And this magnetic field will try to attract the original one. It will be in the same direction as the original field, so it will try to attract it back towards it. Hence, when we remove the north pole, a south pole will be induced here, trying to bring it back towards it. So that means that the other side would be north, and using the right-hand rule, you can find the direction of the current. Going to put your thumb in the same direction as the north pole, and you can see that your four fingers will coil away from you like this. Remember when you drew arrows on your hands, you're going to do that again this turn. So from the side that you see in the solenoid, the current will be upwards. So again, magnet in, we will have repulsion. Magnetic field inside the coil will increase. A current is induced such that it induces its own magnetic field in the opposite direction of the original one, and will try to repel it away from it. magnet out, the magnetic field inside the solenoid will decrease. Hence, a current is induced that induces its own magnetic field and will be in the same direction. Going to be here. So north, let me just stop the video for a sec. Here, you can see that north going like this, south going like this is going to be in the same direction as the magnetic field generated by the magnet or the original magnetic field. And the coil will try to attract the magnet back towards it. Using the right hand rule, be able to find the direction of the induced current. All right, let's answer some questions about Lenz's law. Remember, Lenz's law is just nothing other than reverse psychology. Lenz's law is used to find the direction of which of the following: the flow of power, potential difference, electromagnetic force, or the induced magnetic field. Well, that's to find the direction of the induced magnetic field. It's either to find the direction of the induced magnetic field, you might say it's in the same direction as the original one, or in the opposite direction of the original one, as well as the direction of the induced current. Right, this is another ministry question. Let me try to remove the previous solution. Oh, okay. Specify the direction of the current. So here we have a north pole that's moving away from the solenoid. That means this solenoid will say, no, I want you back, come back, please. How does it do that? By generating a south pole that tries to attract it back towards it. So the other side we will have a north pole. Using the right hand rule, you're going to put the thumb in the same direction as the north pole. Whoops. You'll see that the four fingers curl like this, so the current will be downwards in the part that you see of the solenoid. So it's going to be from B to A. So the current will flow from B to A. Okay. Specify the direction of the current. All right, here we have a north pole being pushed inside the solenoid. It's being pushed towards it. It says, no, I don't want you. Go away. How does it do that? By generating another north pole to try to repel it. So you will have repulsion. Go away, I don't want you. So in this case, we will have a north pole here and a south pole here. Using the right hand rule, if you put your thumb in the same direction as the north pole, you'll see that your four fingers curl away from you. Remember to draw arrows on your hands. So the four fingers, so the current will be like this. So it's going to be from A to B. Specify the direction of the current. Okay, another one. Here we are bringing a south pole in. I don't want you, go away, go away. Okay, so if it's being pushed towards it, gets angry and it tries to push it away. How does it push a south pole away? By generating a south pole so that we have a repulsion force between them. So the other side would be a north pole. Now using the right hand rule, if you put your thumb in the same direction as the north pole, the four fingers will curl downwards. So that's the direction of the current. Going to be from B all the way to A. I might need to remove all of these before I exit. Here we are pulling a south pole out or away from the solenoid. When we take the magnet away from the solenoid, it starts to want it back. No, come back, please. How does it do that? By generating a north pole to try to attract it. So we will have a north pole here and a south pole on the other side. Using the right hand rule, you'll see that the four fingers will curl away. So that means the current is like this from the side that you can see. So it curls like this, goes downwards to B, and like this. So it's going to be from A to B. Right, which of the following, or sorry, when the magnet is approaching the coin, this is the coil, a current is induced in the coil. Which of the following diagrams is correct? I'll start the first diagram. Let's see if it's correct or not. So a south pole being pushed towards the magnet. The magnet, towards this coil. The coil will get angry and it will generate a south pole trying to push it away. Now using the right hand rule, you can find the direction of the current. So here we have a south pole, the other side will have a north pole. Going to put your thumb in the same direction as the north pole. You'll see that your four fingers curl away from you. So the current will be upwards in the side that you can see from the solenoid. And you can see here that that's not the correct direction of the current. So this one is not correct. But let's see the one below. We're trying to push a south pole. The coil or the solenoid will get angry and it will generate a south pole, not a north pole. So here we have to have a south pole. Because if you're trying to put the magnet in, we'll try to resist that. We'll generate a south pole to try to repel it away from it. So here, this is incorrect because we should have a south pole here. Let's say this one. We're approaching south. We should have a south, since putting a magnet in will mean repulsion. And here, this is attraction. No. All right, let's see. Obviously, it's the last one, but let's see if it's correct or not. So we're pushing south, angry solenoid generates south to push it away. So that means that the other side is going to be north. Put your thumb in the same direction as the north. You'll see that your four fingers curl away from you. So the direction of the current from the side that you can see from the solenoid is going to be upwards. So this one is the correct one. All right, let's see this one. What are the poles induced on a solenoid? So here we're pushing a south pole, pushing a south pole in the solenoid. Solenoid gets angry, generates similar pole, try to repel it. So this one will be south, same, and the other one will be north. So that means that X is going to be a south pole and Y is going to be a north pole. Specify the direction of the induced current. Now using the right hand rule, hopefully I've got it here somewhere. Oh, there you go. Using the right hand rule, you're going to put the thumb same direction as the north pole. You can see that the four fingers curl down. So that means that the current is going down in the side that you can see from B to A. All right. What happens to the deflection of the galvanometer? Now, galvanometer measures current, by the way. Okay, it's the same as the ammeter. But it's the difference between it and the ammeter is that it measures very small currents. What happens to the galvanometer's needle's deflection in the following cases? Moving the magnet magnet quicker, well, when you move the magnet quicker, you will induce a larger current, just like we have learned in lesson 1. Quicker means that EMF, remember BLV, quicker means more EMF. And since I equals EMF over R, EMF more, I more, so the current will increase. Putting an iron core, just like we have learned in term 1, putting an iron core inside a solenoid will increase the magnetic field produced by it, and hence it will increase the current as well. What is the direction of the current when the magnet is pulled away? So, oops, what happened? If the magnet is pulled away, so here is South Pole, the South Pole is pulled away, the solenoid will start to want that South Pole, so it generates a North Pole here. So the direction of the current will reverse. So here the current was downwards. When we move the magnet away, the current will flow in the opposite direction, will flow upwards. Or you can say from A to B, which is opposite to this one. Right, this is a similar question. And stop the video and watch it or try to solve it. A rectangular metal loop ABCD is placed in a uniform magnetic field as shown, in which case will there not be an induced current? Well, it's the first one, and it's because you're pulling this loop of wire with a constant speed. And when you move it with a constant speed in a magnetic field, the amount of magnetic field lines inside the loop stays the same at all times. So there's no change in the magnetic field, and hence it will not, no current is generated in the wire. Only when there is a change in the magnetic field will there be an induced current. All right, let's stop here. This is lesson 2.